Beginning as a research program in the mid-1950s at Battelle Memorial Laboratories in Columbus, Ohio, hot isostatic pressing, or HIP, is today used by thousands of industrial companies around the world to improve the performance and durability of a broad range of products and components. This video is intended to provide a basic understanding of the HIP process, its benefits, and its many applications. Hot isostatic pressing is a forming and densification process using heated gas under very high pressure. Unlike mechanical force, which compresses a workpiece from one or two sides, isostatic pressure is applied uniformly on all sides of an object, eliminating porosity without changing its net shape. The process can be used to treat preformed metal, ceramic, or composite parts, and for compaction of containerized powder shapes. Over the years, hipping has proven its ability to significantly improve the physical properties of parts used in higher stress applications. Hipping provides the following specific benefits: densification of powdered metal parts to 100% of theoretical density, total elimination of internal porosity in castings, improvement in mechanical properties. These include increased resistance to fatigue and temperature extremes, higher resistance to impact, wear, and abrasion, and improved ductility. Hipping typically leads to more efficient production. Near net shape forming to precise tolerances means little or no secondary machining or manual rework. The scatter band in measured properties is reduced, and scrap loss is decreased. Hot isostatic pressing can also provide cost-effective diffusion bonding or cladding of dissimilar materials. The need for long-lasting, high-performance components exists in a countless number of manufactured products, and hipping is employed in a number of major industries, including automotive, aerospace, military, heavy equipment, industrial machinery, marine, oil and gas, and medical, among others. The materials that most commonly benefit from the hipping process include superalloys, high-speed steels, stainless steels, titanium and aluminum alloys, refractory metals, carbides, engineered polymers, advanced ceramics, cermets, ferrites, and many types of composite materials. HIP presses are offered in a variety of sizes, depending on the application. Compact laboratory units are designed for research and prototyping, while large HIPs handle higher volumes as part of the plant's regular manufacturing operations. Work zones inside the cylindrical pressure vessel range from 3 inches to over 5 feet in diameter, with heights from 5 inches to more than 10 feet. Maximum standard operating pressures can be specified from 1,500 to 30,000 psi. Higher pressures can be provided for special applications. Several types of modular electrical furnaces are available to handle varying part materials, atmospheres, and heating requirements. Maximum temperatures are typically in the area of 2,000 degrees Celsius. The operational steps in running a HIP cycle are essentially the same with all machine brands, although users should always take care to follow the manufacturer's specific instructions and cautions. Parts such as these castings are commonly loaded into some form of metal basket, which is then lowered into the furnace positioned in the pressure vessel. While this vessel loads from the top, some presses feature bottom-loading systems. An insulated thermal barrier surrounds the furnace to focus the heat load on the parts and away from the water-cooled vessel wall. The pressure medium is most commonly argon, which is fed from storage cylinders to an electrohydraulic intensifier that pressurizes the gas to the required level. A system of high-pressure feed and vent valves controls the flow of gas to and from the pressure vessel. The self-sealing vessel closure assembly is lowered into place, and from this point on, the press is typically controlled by a computer which follows a recipe programmed by the user. The program determines pressure and temperature ramp-up, the preset soak time, depressurization, and cool down. Cycle times vary from 2 hours to 8 hours or more, depending on part materials, work zone size, and other variables. The production of powdered metal components is one of the major applications of hot isostatic pressing. Powdered metallurgy creates specialized alloys with a fine-grained microstructure and uniform purity. The alloy powder is loaded into precisely designed metal molds, which are then welded closed and evacuated to create an internal vacuum. The HIP process shrinks both the mold and powder, fusing the particles into a precise net shape. The elevated temperature imparts strength and cohesion to the part. In most instances, this simultaneous application of pressure and heat can eliminate the need for secondary machining or sintering operations. Hipping is also employed to improve the performance of cast metal parts. A large number of castings can be processed in a single cycle. Internal porosity is totally eliminated, and the hipped parts typically have properties that sometimes exceed those of more costly wrought or forged products. The original HIP, developed at Battelle Labs, was commissioned by the Atomic Energy Commission to bond the elements of nuclear fuel elements. Today, diffusion bonding remains a common application for hipping of high-performance components. Dual metal parts are created by cladding a layer of corrosion or wear-resistant alloy to the surface of a bimetal component. Decades of successful experience have proven that hot isostatic pressing is the premier method of producing the strong, long-lasting products that are increasingly demanded by globally competitive manufacturers in all kinds of industries.